Okay, let's dive right into this explainer and build a high-utility visual playbook for Grafana Loki. If you're managing complex systems, you already know logs are your ultimate source of truth. But let's be real, they can also be an absolute overwhelming flood of text. So today, we're going to transform that wall of text into targeted, actionable intelligence using LogQL. Picture this. A production alert wakes you up at 2 a.m. Your brain's a little foggy, but speed is absolutely everything right now. How fast can you go from that blaring pager to actually pinpointing the root cause? Well, the answer comes down to how effectively you query your data. Mastering LogQL, which is Loki's native query language, is literally your fastest path to the answer. It's the difference between a frantic, hours-long search and a precise 5-minute resolution.
Here is our game plan for today. First, going from alert to root cause fast. Second, selectors, contains, and regex. Third, parsing and label filtering. Fourth, metrics, rates, and top K. And finally, a live demo debugging a massive spike in 500 errors.
Let's kick things off with part 1, alert to root cause fast.
Now, Loki's whole underlying philosophy is to index little, grep a lot. Traditional logging systems heavily index the full text of every single log line, right? And that gets super expensive and incredibly complex to manage at scale. Loki, on the other hand, only indexes the metadata, the labels. That makes ingestion blazing fast and storage incredibly cheap. But to write efficient queries here, you've got to clearly separate your stream selectors from your pipeline stages. The log stream selector uses those indexed metadata labels to instantly locate the right streams of logs. Then your log pipeline takes over. That's where you filter, parse, and mutate the raw log lines. Understanding this separation is absolutely crucial for performance. You always want to use your selectors to shrink the haystack before the pipeline starts looking for the needle.
Moving right along to part 2, selectors, contains, and regex. Every single LogQL query kicks off with curly braces. That selects the exact stream of logs you want to investigate. Here's pattern 1. We're looking for app equals nginx, namespace equals prod. This simply tells Loki to ignore everything else in your vast infrastructure and just grab the logs matching these exact labels. It is the absolute foundation of every performant query. Now, for matching those labels and filtering lines efficiently, we've got a literal cheat sheet of operators. We use the equal sign for exact matches, and exclamation equals for inequalities. For line filters, the pipe equals means the raw log line contains a specific string, say error. An exclamation tilde? That's a negative regex filter. It's incredibly powerful for throwing out noisy, repetitive stuff like health checks. You are definitely going to want to memorize these operators. Let's actually combine them. Here are patterns 2 and 3. By chaining a contains filter with a negative regex, we instantly narrow our results to actual errors, completely tossing out the noise of known timeouts. But notice the order here. We select the stream, we do a super cheap literal string search for error, and only then do we apply the much more CPU-intensive regex exclusion. Literal string searches are highly optimized. This whole filter early principle, reducing your data volume before running heavy operations, is exactly how you keep your queries lightning fast.
All right, part 3, parsing and label filtering.
Loki's schema at query capability is just fantastic. By piping your query straight into the JSON parser, you instantly transform raw, unstructured JSON text into clean, usable labels, things like level equals error and duration equals 150. The beauty is you don't have to rigidly define this schema or build some massive ingestion pipeline when the logs are first written. You define it exactly when you need it during your investigation, which saves massive amounts of indexing overhead. And once parsed, you can apply label filters post-parsing to isolate really specific conditions, like, say, finding requests taking longer than 100 milliseconds. Applying patterns 4 and 5, we select the job, parse the JSON, and then mathematically evaluate that extracted duration. This is a complete game changer for tracking down latency bottlenecks or dynamically filtering for specific user actions.
Section 4. Metrics, rates, and top K.
So logs are obviously great for reading line by line, but metrics are what you actually need for graphing trends, spotting anomalies, and firing off alerts. Enter pattern 6. Wrapping your log query in a rate function over a 5-minute window instantly calculates your per-second error frequency. Just like that, we've turned a basic text search into a mathematical rate. It totally bridges the gap between logging and monitoring. In fact, this exact query structure is what you'd use to build dynamic dashboards or trigger those critical production alerts.
Then we have pattern 7, the top K function.
It instantly ranks and exposes the absolute noisiest failing services. Look, when everything is on fire, TopK is your best friend. We can instantly see the checkout service is throwing 45 errors a second, completely dwarfing the others. You don't have to guess where to start investigating. The data literally hands you your priorities.
Which brings us to part 5, our live demo, debugging a spike in 500 errors.
Imagine this scenario. PagerDuty just woke you up because massive 500 HTTP error codes are spiking across your entire production cluster. Your dashboard is just a sea of red. So where is the fire actually starting?
To isolate the exact failing pod, we're going to compound our cheat sheet patterns methodically. Step 1, write the stream selector. Step 2, add a line filter. Step 3, wrap it in a rate aggregation. And Step 4, isolate the culprit with TopK. Let's actually execute this play. Over in the Explore tab, we type our stream selector and a literal line filter. This instantly brings up matching red log lines. We've basically grabbed all production logs and filtered them down to just the ones containing the exact string status equals 500. Now it's fast, and we're definitely looking at the errors, but we need the bigger picture to find the actual source. So, by adding the rate aggregation, we shift our entire view from raw text logs to a real-time error frequency graph. We're now calculating the rate of those 500 errors over the last 5 minutes and summing them up, grouped by the application name. The shape of the problem is finally becoming clear. Finally, wrapping that whole thing in TopK instantly isolates the checkout service as the definitive root cause of our massive 500 spike. Boom, right away, the checkout service spikes to the top of the graph. In just 4 logical steps, we went from a cluster-wide panic to pinpointing the exact failing microservice.
Keep this visual playbook handy, make sure you grab the downloadable reference card, and remember, the golden rule: always filter your data early for the fastest results. Maintain strict label discipline. Keep those initial selectors narrow. Run your literal string filters before your parsers, and just extract what you need on the fly.
Which leaves us with one final thought. Once you master LogQL, you stop treating your logs like a giant text file that you have to manually comb through, and you start treating them like a dynamic, queryable database. What hidden anomalies and insights will you uncover in your own infrastructure when you stop merely searching and start truly querying?